So I guess that's a good thing. So those are the sections that we'll try to go over. I don't think I hear y'all too well, so please interrupt if you need to. Basically, the sBitX is a fairly groundbreaking, very inexpensive hybrid SDR HF radio. It's not up to the latest specs of some of the fancier equipment. It does not include both the I and the Q 90 degrees out of phase demodulation tracks, but it does manage to demodulate and modulate, all done in math, which is done with Fourier transforms, fast Fourier transforms. The current version is selling with a Raspberry Pi 4 processor, but I understand this can actually run on a 3B plus, and smaller versions are running on the Pi Zero 2. I get all their numbers mixed up. The front panel has a touchscreen. FT8 and FLDigi are built right in. What's really nice about it for those of us who are on the air is it has fantastic digital filtering. In some ways, I've liked earlier versions of its digital filtering even better than 7300 ICOM. They've changed a bit of that. Other people have reverted back to the older ways. It's just an amazingly nice receiver. It's a hybrid SDR. For that price, I think they go for about $399 new. Already built. It's not really a kit. You don't get FPGAs and high-speed A to Ds. You get regular stuff. So the incoming signals are heterodyne down to the 25 kilohertz range. Ultrasound and then a common audio codec is used to do the A to D and D to A, and all of that is under control of the Raspberry Pi. So they took advantage of some inexpensive techniques to do SDR. It's similar to some of the higher end satellite radios that heterodyne down from the gigahertz range to get within where they can actually do A to D, D to A. So when I talked to you last year about this unit, and I was very surprised that that talk has seen 2,900 views. I didn't expect that. Being chintzy, I had a used version 2. I didn't buy one new. I found one used. I already had a developer's edition, and I'd been using the developer's edition for a good while. On the used version that I purchased, we had some problems. There were some really bad harmonics, really bad problems coming out. And what it turned out to be were shorted diodes in the control circuitry, which were possibly my fault because they were rigged in such a way that if you made a wrong move with a test probe, you could easily put a huge amount of 12-volt current through them. I'm not sure when that happened, but they were certainly blown. So when I replaced them, I put a few resistors in series to provide some protection for those surface mount diodes in the future. At that point, W9JES had provided some software that allowed some external application control of frequency and other techniques, which I took advantage of. And I had created an external interface to allow an emulation of the ICOM 7300, which was not a full emulation, but it was enough to where I could run WinLink with an external computer going into the sBitX. I could control the frequency and operate it just as if it were an ICOM 7300. In order to do that, I used some RS-232 to 5-volt TTL adapter cables between the units. Someone on the YouTube pointed out that there might have been a UART on board that I could have used, but either I didn't know how to do it or I didn't think of it. I had managed to find an RFI-free commercial power supply. These commercial power supplies have gotten way more expensive. So I managed to find one that was cheaper, and I got that going. I had my own homebrew Go box. I build these things out of plywood. I don't plan to go through the Amazon River with my equipment, so I don't really need to make it waterproof. And I had outfitted that with a signal link and an auto antenna tuner, and I was just doing great. I was having all kinds of fun. To do some of the stuff that I did, I had added a few extra connections and outputs to the sBitX. I provided an audio output jack that allowed me to get external sound cards connected. And I worked on a push-to-talk optocoupler system that creates the equivalent of a relay output for the sBitX, so you can activate a linear amplifier, which in this case I use a lot with the sBitX from North Carolina. I added some polarity protection on the power line. A good number of folks destroy radios, expensive radios in many cases, by accidentally getting the battery clips on the battery backwards or having some other small boo-boo. And so I think polarity protection is pretty important. I'd also added a few extra doodads in my Go box so I could monitor the RF output and see the DC current measurement, which was real simple. It's taps a few inches apart on another number 16 power wire. In the right-hand side of the screen, you can see how I did the send output. I used an optocoupler to completely isolate the two systems. And I learned the hard way, you never want to connect to the analog plus 12 volts of the sBitX design, because you introduce all kinds of RF issues and dirty up the output pretty badly. So instead, you prefer to use digital signals in the sBitX and use those to do all your control. It's exactly the opposite of what I would have thought, but it worked fine. At that point, ARRL had a fair number of folks, nobody knows for sure how many, blow out their IRF Z24Ns in their sBitX version 2s, which is what I had. It's a 50-volt MOSFET device, and they had a good number of those blow out. So he switched back to the IRF 510, which is an older device, which has a 100-volt drain source rating. And he decreased the gain in certain parts of the stages because he assessed that he'd had gate failures due to high voltage oscillations reaching the gate of his final amplifier stage. And he thought he had a more rugged unit. On the BitX20 forum, I haven't seen nearly as many people complaining of blown MOSFETs after he made that change. So from a manufacturing standpoint, I think that was a pretty wise decision for him. However, I wanted the more headroom on 80 meters and 40 meters so I could run digital without much limitation on linearity and get a bit more power. These circuits are surface mount, and they're quite an issue to work on. Even though the sBitX was built with fairly large surface mount that you can actually work on with tweezers, I was still using some pretty large Zener diodes on the gates. Those had a pretty high capacitance, and so that reduced the amount of power that I could get on higher frequencies. On the right-hand side of this slide, you can see what ARRL put out as power that he was getting out of his version 3. He could get 25 watts on 80 meters and 40 meters and 30 meters, and then his power started to go down. And he ended up with 9 watts on 10 meters. Okay. This came out just before the last TECHCON, and he had improved a good bit of his software. There was better connection to the codec. Codec connections were less flaky, and he had gone down slightly in power. Better documentation was available, and this was a bit more robust unit for sale. I was still doing fine with my RFC 24Ns, getting a little bit higher power. I was up in North Carolina, and I had it connected to my SB200 vacuum tube amplifier without an intervening antenna tuner right at that moment. The SB200 has a tuned input, but it's not too good at the 75-meter end of 80 meters. And I sent just a few DITs with Kier while I was looking at the SWR, and bingo, all of a sudden my sBitX goes completely blank. The unit is dead. And remember, I told you I'd added that current meter, which hadn't been working all that well, but all of a sudden it was showing I was drawing huge amounts of current. So one of the two finals had shorted out. When I did some work on, I think it was the lower of the two, and it was completely dead shorted out. And I'd been using sBitXs for quite a few years, used microBitXs before that. This was the first MOSFET I'd ever blown out, and I had no idea why that had happened. I couldn't imagine, because I had set all the proper levels inside the unit, and I just had no idea how that could have happened. It wasn't set for completely full power. It was slightly lower than full power. It should have been fine. So my question was, what do I do now? What do I replace this with? So I could just go ahead and put in back IRFZ 24Ns, but that would risk a repeat of the failure, which I really didn't know why it had happened. I could downgrade to Osher's choice of the IRF 510 and make the changes that he had made to the driver circuitry and reduce a bit of the gain in the driver circuitry, which was built to drive the really high input capacitance of the IRF Z24. A lot of people were using the IRF 520. It has a 100-volt drain source rating. It's the same 20-volt gate limitation without any built-in protection. If I were going to do that, I would probably switch and use the TBS diodes that Osher claims are faster than Zener's. I'm not completely sure I agree, but Osher knows a good bit of radio, so he may well be right. So I had to go through a process of trying to figure out which do I want to use. Of course, the expensive units use made for RF MOSFETs, but I was still part of the revolution trying to use cheaper MOSFETs for this. All three of these MOSFETs are hex FETs, and I've got a drawing here to the right that shows you sort of how they're built. The gate structure is in a geometric design with metallization and insulation, silicon dioxide between it and the channel. And there are some really odd effects that can occur in this that I really wasn't aware of until I actually started putting this talk together. It turns out there's some inductive effect in the gate structure, and you can actually end up with some resonances in the gate structure because of that inductance and the capacitance of the metallization over the silicon insulation. So there's some really complicated things that go on with these MOSFETs. They're not completely innocent devices. This is a warning that's published with one manufacturer's device, Infineon. Even if the applied gate voltage is kept below the maximum rated voltage, the stray inductance of the gate connection coupled with the gate capacitance could generate voltages that could lead to the destruction of the oxide layer. They recommend against Zener's, which they actually think could contribute to the oscillations. And they recommend putting a series resistor in the gate circuit to reduce these oscillations. So they're aware of these problems, and it's a little bit tricky to know how to prevent these problems from occurring. So I was sort of torn between the IRF 520 and the IRF 510, which Osher had gone back to. They're both 100-volt devices capable of taking most of the bad SWR effects that you can get from a bad match on the output. They both have a 20-volt limit on their gate insulation. The input capacitance of the 510 is twice that of the incapacitance of the 520. So it really looks a lot like it's just twice as much die area as the 510. The resistance of the 510 is higher than that of the 520, also suggesting that the 520 is just a larger die, and the 520 is capable of handling a bit more power than the 510. Might also have a little bit better thermal connection to the tab. So I was really kind of stuck as to, well, which do I want to use? Here are some of the specifics on those two devices. The 520 has an RDS on of 0.27 ohms. The 510 is just twice that at 0.54 ohms. The gate capacitance of the 520 is 360 picofarads, which is twice that of the IRF 510. The IRF Z24N, which version 2 was designed for, was even a tiny bit more, 370 picofarads. So basically what Osher had designed for, the 520 would be a pretty good fit for what he had designed for, and it offered twice the drain source voltage protection. The V3 circuitry, which is currently being sold, would not be a good fit for this because it's not designed to drive the input capacitance of 360 picofarads on each device. So I elected to go ahead and put in the IRF 520, and the picture at the right, you can barely see them. I'm not sure if you can see my arrow, but these two arrows in my arrow are pointing at one of the TVS diodes. These are the protection diodes that Osher recommends. They are really tiny surface mount devices. They're just terribly tiny. You can see by comparison a quarter of this. I think it's either a quarter or an eighth watt resistor there. Getting these into position, scraping off a little bit of the resist coating on the top of the trace, getting those soldered in. This was quite a trick. They clamp at about 13 volts. Their working voltage is listed as 8 volts. They're bidirectional. And I think they have lower capacitance than the big 5-watt Zehners I had been using. But if they do, it's basically just because they're tiny. And because they're tiny, they have lower capacitance when they're not conducting. But I went ahead and did that because that's what Osher had picked, and he's been fairly successful with it. So here's what happened when I did that. This table shows you the hardware settings that I picked. It's a gain factor that's used inside the software of the sBitX, and I didn't push this device as hard as you might could push it. So these output levels are intended to be within the linear range, but I'm able to get 32 watts out on 80 meters, 33 on 40 meters, starts dropping 22 on 30 meters, 16 on 20 meters, and then I'm still getting 11 watts on 10 meters, which is a good bit better than what Osher's able to get with his V3. And it's actually better than what I was getting on that band with the Z24N, where I had the large Zehners on the gate as protection. The curves, the curves that are presented in manufacturer specs are on log-log scales. And because they're on log-log scales, it's very hard to do what we're used to doing in the past, draw a linear load line for the expected impedance that the device flows into. Because on a log-log curve, a straight line ends up being a curve. So I attempted to show you the load line that my device is probably running at with an estimated 5 ohm load resistance applied to the MOSFETs. There's then a big step up transformer to drive the 50 ohms of the antenna system, but the load line ends up really confused because it's it turns into a circle on these kind of plots. You really don't use most of the region of the MOSFET when you're using it in an RF surface. You only use a portion of its useful range, and they tell you that you're using the linear portion, but I'm not completely convinced of that. These are definitely not terribly linear devices, so you definitely are required to use a good bit of filtering. However, I ended up with a device that seems to work fine now. I haven't been able to get on the air as much as I'd like, but I've not been able to destroy it since I put in the IRF 520s. It's been working fine for me. So I was very happy with that. I purchased a second V2 off of another person used. Normally, I upgrade these by changing out the mica insulation between the MOSFETs and the heatsink and replace it with aluminum nitride and get much better thermal characteristics. So I have some work to do on the second one, which I haven't gotten to yet. And I may or may not switch out its MOSFETs because I now have a nice stock of IRF 520s, and I was pretty happy with those. An issue that we were still having trouble with middle of last year was Morse code. The V2 had just a wonderful diode switching system, not like the relays in an ICOM 7300 that just drive me nuts. So it would switch between transmit and receive very nicely, but it just had terrible issues when trying to send Morse code with an external key. It was extremely jerky. It was so bad that my external keyer, I thought it had a bad relay output because it just wasn't sending the right code. It would just not follow what I was sending at all. This made it impossible to use the Win keyer. I'll be talking about that later today, why you want to do that if you're a CWOP. It made it just very difficult. So it was so bad, the delays and the jerkiness were so bad that I thought my keyer was defective. It turned out that wasn't the case. So Mike, I think his name's pronounced John Choi, KB2ML, did a deep dive into this and figured it out. In Osher's software, he did a polling technique to check for the status of the straight key input. His code for the paddles was actually a fair bit better, but his code for the straight key input, which is what you need to use if you're using an external keyer, has just big delays in it. So Mike calculated what the length of a dit was, just the dot element in Morse code at various speeds. And you can see it gets to be pretty short. And Osher's code was only checking once every 20 ticks for this. And so it turned out that at 50 words per minute, which I can't do, you were only checking once during a dit. And if you were running at 25 or 30, you were only sampling maybe less than twice the number. So doesn't even meet the Shannon requirement. And you're certainly going to have huge delays. So this explained the jerkiness of the coding completely. Mike recommended a change to the coding that would, instead of waiting 20 ticks to check the CW key, would check it when you were in Morse code on every single tick of this timer inside the sBitX. So that would get you a lot more frequent check of the Morse code key. So I implemented that and it works great. It's just fantastic. So if you have that running, the straight keys now work perfectly. External keyers, this is the Win keyer in the picture here, work perfectly. So he fixed that part of the problem. The next part was there was a big delay when going from receive to transmit. So your first character got clipped. So dashes became shorter and dots would almost disappear. And it turned out that Osher had put in a very large delay there as well two different delays and maybe a little bitty another delay, 10 and 20 milliseconds. So the receive to transmit state transition was just really long. And it was very hard to use this in contests because the first character was so badly mangled. This may have been related to the work Osher was doing in trying to figure out turn-on oscillations in the transition state between receive transmit and transmit receive. It may have been left over from that, a problem that I believe has been completely fixed. So was there a question? Not hearing anything. So I went ahead and tried much less delays, and other people have done this as well. This is the original code, which shows a delay of 1 millisecond here. There's another 2 millisecond delay here, 20 millisecond delay here, 10 millisecond delay here. I took those delays down to on the order of 5 milliseconds, and I saw no problems at all. I looked at the output, I looked at the signal with an oscilloscope. There was no hint of any oscillation on any band in my V2 unit. So I was pretty happy with that. And I picked middle ground delays, and unfortunately I haven't been able to check and see what delays I did pick, but I think they're under 10 milliseconds total. And as a result, the turn-on delay is now minimal, and the unit goes into transmit very rapidly. And you can operate it at 25, 30 words per minute without any problem in a contest. So that was a big improvement. The next problem that a lot of these units had were receiver birdies. There were a lot of spurious responses. Now, all receivers have these. It doesn't matter what you've got, it's going to have some spurious responses, signals that really aren't there, but they come up and you can hear them. They occur because of intermodulation effects between harmonics of all the various oscillators. And because Osher chose a hybrid SDR with heterodyne oscillators, he's got a lot of oscillators in his system. So there's lots of ways that you can get the seventh harmonic of this with the sixth harmonic of that, combining to provide a note that's within the ham band. We also have power supplies that have switching systems and 5-volt regulators that have switching systems. He's also running microprocessors, clocks, and displays. These birdies are more obvious when you have no antenna input and there's no signal. Normally, if you connect up a normal antenna, they're pretty well masked, not always, but most of the time by the normal galactic and lightning background levels. But they're still somewhat bothersome. Now, I have not been able to do this yet on my unit, but W9BLW really worked at this and worked at insulating and that's not the right word, worked on shielding different parts of the sBitX inside the case. Here you can see an sBitX taken apart, and the top part here that you can see is the display portion, and then below you can see the RF portion. He has picked the receiver portion on the bottom, built an insulating plastic cover, and then covered it with copper tape to add more shielding. This was a prototype effort. Other people and Ryan have done this, and they found that one of the chief offenders is the ribbon cable that goes to the display. So what I plan to do is first shield that. This is some copper tape applied around it, and then I'm pretty sure there's transparent layer of insulation on top of that so you don't short things out. And if you can do this also with the kind of tape that air conditioner people use. It's a real aluminized duct tape. And if you do that, you get a great reduction in the birdies of this unit. So that's sort of a nice fix that home brewers can do to a commercial receiver and make it work a good bit better. Well, the community of sBitX users has been very productive in the last year. And JJ, I think it's W9JES, has really done a lot of work, and he was most offended by the 32-bit code that was being used on the operating system and in the sBitX, which is still what I have. So he came out with a 64-bit set of code on the upgraded 64-bit operating system for the sBitX. His code has been very well received. A large number of people have switched to it. I have not yet made the switch myself, and I don't think HF Signals has made the switch either, but it's been very well received. I've looked through parts of his source code, and he did make the changes in the delay codes, in the CW delays that have been recommended. So I think people who have switched to his code are having much better CW performance without having to do any coding themselves. So I think that was a place where the user community has really helped this device out a good bit. Well, then the big surprise came. There had been some lead up sort of planted questions. How many people would be interested in a really small version of the sBitX that was really intended to just carry with you into the woods? So ARRL has developed, and this is an early photo. We don't know exactly what the final unit's going to look like. An sBitX built in a much smaller fashion with even smaller surface mount devices. It's not intended to operate on 12 volts. It's intended to operate on about 6 or 7 volts from 2 LiPo cells. And it uses smaller output MOSFETs, basically puts out about 5 watts. You can crank it out to 10 on some bands if you provide a little more power to it, but it's not intended to operate at 12 volts. And it's basically the same software. So there's a good chance that this will come out with a 64-bit software. And I believe he set a price of $199 for this entire HF transceiver, which is sort of a G90 competitor from Xiegu. Lower power, but even more compact and offering a bigger screen. And, in my opinion, really nice software. So this got very well received. They took in orders for just a couple of weeks, and then they shut off orders because they had already gotten 400 orders, and they didn't even have boards yet because of the Chinese New Year. So they shut off ordering until they could catch up with the demand. And now the big deal is everybody's asking, when are you going to open up and take more orders? Because I want to order one of those things. Well, it's not my cup of tea, but everybody else seems to like this unit. And so I think this is going to be a big success as well. And hopefully some of the things that we learned from the sBitX have been incorporated in this. So we'll have maybe a few less teething problems getting the new units out. The idea is that he may be shipping units towards the first part of March. There have been some delays, problems getting materials due to the Chinese New Year. Okay, well, what have I been doing? Well, before I hurt my knee, I was really starting to have fun because our Aries group has been doing winter field day and summer field day, and we're getting better and better and better at it, which I'm going to talk about in another talk later today. But we only really had one guy who knew how to do satellites, and he could never seem to get us a contact. I think I understand why now. It's terribly competitive, but I wanted to learn something about satellites, and I just didn't have a way to do it because I had no units whatsoever that could operate linear mode, single sideband CW on UHF or VHF. And the Ukrainian folks have been selling these things for forever. And so I decided to order one of these and give it a try. And it has been a big success. So I have some information to tell you about that. So I thought using this with the sBitX was a marriage made in heaven, because the sBitX gives you the pan adapter type display over about 50 kilohertz that really allows you to see other signals in a good bit of the passband of a linear satellite. And mine had an output push to talk relay control. The sBitX has plenty of power to operate this thing. Most of these are made to work on milliwatts of input, and they have to have a built-in attenuator to operate on any more power than that. So when I got mine, this is the inside of the transverter. A Ukrainian transverter comes to you already built. The one I purchased was sort of more expensive. It was designed to operate on both 2 meters and 70 centimeters. It does both directions, receive and transmit. And it came built with a Vox system, voice operated. It detects incoming RF and automatically goes into transmit. That didn't work as well as I would have liked. It turns out the gain of this device is sort of high on 2 meters, and that 50 ohm input resistor right there and the attenuator circuit right here, the gain is so high that you just can't run much power into this thing before you're already saturating it. So it only takes less than a watt on 2 meters to provide full output from this device. And it doesn't activate the push to talk as well as you would like. So if you're doing digital, it will stay in apparently. But if you're doing single sideband voice, which I was trying, it would click in and out while you were talking because the single sideband signal has louder and softer parts. And in the softer parts, it just didn't stay into transmit. So I discovered how to get to the fancy little semiconductor. They actually use a voltage regulator as a switch, and I managed to connect to that and run some wires out from that, so I could have a push to talk input. Other people had recommended this, and I was easily able to control this from my modified sBitX, and it just works fine. This is a real RF MOSFET here. You get about 10 watts output on 2 meters and 5 watts output on 70 centimeters, reasonable linearity. These things are tiny. This is a regular tumbler glass of iced tea, and this thing is just tiny. I was able to, this is kind of my jumble of my ham station, with an sBitX, and I lost the microphone for the sBitX. It's somewhere in all of my junk. So I had just a mess of adapters so I could operate with a amplified CB mic. And here's a VHF, UHF watt meter. Here's my polarity protection, and there's the SB200, and there's the transverter right there going off to some big LMR 400 coax. And bingo, using this homemade 3-element beam that you can see here, which was built to be a vertical beam, but my friend 11 miles away has horizontal, so I had to lay it on the banister and on a chair, and I was able to hold without any problems a 2-meter single sideband QSO with my friend 11 miles away, which is pretty impressive. Single sideband offers big advantages over FM for low signal detection. It doesn't have the need for a strong signal in order to capture the frequency. Single sideband does much better at low signal levels. So I'm like, this is a success. This works. You can now do local single sideband with just an sBitX, which you might already have, and a cheap Ukrainian transverter. But if you want to go on to do satellites, that's a bigger issue. Little bit more of a problem. Now, there are available commercial ICOM rigs for, if you got $1,700 laying around, that will give you dedicated duplex VHF, UHF satellites. Using a couple of sBitXs and a transverter or 2 transverters might be a lower cost method to get into this. And it also might not work at all because I've never done this, but it's fun working on it. And so I've been working on how can you do this with the sBitX. And so I've spent a good bit of effort trying to figure this out. If you're trying to do satellites, and some of you probably have this experience, which I have not done. I've watched these people try it and seen how much trouble they have. you not only need to be able to control your directive antenna, two directive antennas, hopefully able to control them in both azimuth and ideally elevation at the same time. There's an issue that the polarization shifts due to passing through the ionosphere, and there is some advantage to using crossed Yagis and wiring them up to do right-hand circular, which gets around the 20 dB loss you might have if the polarization shifts 90 degrees to what your single polarized Yagi can do. And if it turns out the satellite ends up in left-hand circular, you're only a 3 dB loss compared to right-hand. So it's much better if you can get circular, but a lot of people have had a lot of success with just plain old horizontal or vertical Yagis and gotten away with it a good bit. The second problem is Doppler shift, because the satellites are effectively coming towards you and then going away from you. So there's a Doppler shift on both your signal getting to the satellite and a Doppler shift on the signal from the satellite coming back to Earth. But the sBitX is cat controllable. So right off the bat, it offers a fairly obvious way to provide cat control of the frequency and get around the Doppler shift. The only issue possibly is we don't have that much power out of these transverters, but I've actually poked around on the AMSAT web page, and it turns out 5 watts is plenty to make some contacts on these satellites, maybe not during field day when people are being somewhat less polite to each other. But most of the time, these transverters appear to be enough to do this. The sBitX makes this Doppler correction easy. It directly accepts on TCP/IP port 4523 commands to set the frequency. In fact, ARRL has apparently programmed it to act like a famous daemon program, rig control, RIGCTLD, that accepts these commands on that same port. And there's a free program called gPredict that is able to track satellites, tell you exactly where they are, point your antennas at them with rote control, and use rig control to adjust the Doppler shift. All of this is free. I was just shocked that it was that easy. So I wished I were there and I could set it up and let you see this run in real time, but unfortunately I'm stuck at home in this easy chair with crutches beside me so I can get up when I need to. So I can't really run this, but it's amazing. The first thing I did was download gPredict and get it working. I don't have it on this computer. I have it on my other computer. And once you get it set up and clued into which satellites you wish to track, it's very easy to see where the satellites are and when you're going to next see them within range, what their footprint is, what their frequencies are, all this kind of stuff. And I was able to take gPredict and I was able to install rig control, which is free, and it's available in both Windows and Linux versions on my computer, and I was able to get that to control ICOM 7300, and you can sit there and watch it doing the Doppler corrections as if you were receiving the signals from the satellite. I'm just simulating it. So then I said, well, that's great, but I had to use this complicated rig control daemon to get this to work. What happens with the sBitX? So the sBitX has a huge advantage because it is a computer. So instead of having to use an external computer, which I had to do for the 7300, you can download gPredict. In fact, it turns out it's already on the sBitX. I was stunned to find it right there, already installed. Get it configured up, which did require an external monitor because the screen on the sBitX is not large enough to get to some of the buttons that you need to do to configure it. But once I connected up an external monitor, I could easily set this up. gPredict runs on the sBitX at the same time that it's running the sBitX program, and it outputs to port 4523 the corrections for Doppler. and the sBitX intercepts those. No need for you to install rig control, and it automatically makes the corrections, and you change your downlink frequency automatically. You are able to specify what your local oscillator is in your transverter, or none at all if you're receiving direct, which the sBitX can't do, and it just works. So once I get a directive antenna set up, I should be able to immediately begin receiving these satellites and hopefully begin to be able to make some satellite connections with the sBitX. Whoops, what did I do? Sorry, I did something. Okay, now you need to control the antenna as well. And it turns out there's at least two ways to do that. So there's a company that German designed this device, which can intercept the output of ROTCTLD, rote control, another piece of free software that can be driven by gpredict, and it can then speak the language of several different commercial rotator boxes, and it can control, it can control Yaesu and other rotators for about $200, which is a lot cheaper than some of the other solutions that are out there. But poking around, the sBitX crowd said, "Are you sure you need to do that?" And it turns out that, well, this is how you would do it if you use the ERCM device. It's a dual axis device. The sBitX does all the trig inside gpredict, puts out an ASCII code that goes in on a USB port to this gentleman's equipment. And this has a couple of different ways. It can output either directly to a Yaesu controller, or he has a small, relatively inexpensive card that can control directly to the motors and read the potentiometers and tell positioning. So you can do dual axis control with this product. But there's another way to do it. So it turns out that the same guy, Anthony Good, who did the Arduino software that I'll be talking about later today, also has rotator control software for an Arduino. And so on the sBitX, you can, on its Raspberry Pi, you can run gpredict, which will do all the trig calculations and send to the TCP/IP socket. And then you will need to run rote control on the sBitX, but that's not too hard to do. It will then output USB controls, and those can be read by the Arduino controller with K3NG software, and it has the ability to speak to a Yaesu. It can also speak to an EasyCom if that still exists, but it can also directly control motors if you put in a relay or a good MOSFET, and it can read the potentiometers and do all the controls needed to do position sensing of a dual axis satellite controller. And this is basically done with an Arduino. So if you're handy with your abilities, some of the circuit boards I've built could almost do this right now, and I'll probably design another circuit board that will be a double axis satellite rotor controller using K3NG software. This has been, I think, produced in the past, and cards were available at some point. I think those people have quit doing it, but I may take it up. So then the last thing you worry about is, well, what about signals? Because a lot of these satellite guys use very expensive preamps placed right next to their antennas to get stronger signals. But there's an advantage if you're using a transverter, because the transverter basically is its own receiver, and you could mount it right up at the antenna. And then what you're coming out from it with is coax. It's only running 29, 28 megahertz, much lower loss. And you can run the signals over to your sBitXs with much lower loss coax and have 25 kilohertz spectrum on each one. So actually this kind of makes it cheaper too. So I'm not sure how much filtering you're going to need to do to protect the two transverters from each other, or if you just run half duplex, it's not nearly as nice. But I think this has some future for us as a lot of fascinating experimentation that can be done to get people on satellites. So where are we right now? Well, we've certainly got a commercial success, maybe not in the same range as Zygu, but we have a very cheap HF hybrid SDR radio, the sBitX. You can buy it as a $180 board alone and then add your own Raspberry Pi, your own display. You can use any display you want because it also works with a mouse just as well as with a touch screen. Or you can go all the way and buy the $399 25-watt hybrid SDR, which has a 25 kilohertz spectrum visualization. ARRL really has the spurious emissions under control. The 100-volt MOSFETs that he and I are both using now, much more robust. I think he solved his oscillation issues and solved his gate destruction issues. He's so confident he doesn't even put the TVS diodes in his current product anymore because he's managed to massage where the gain is so he doesn't think it's an issue anymore. For me, I kind of like those TVS diodes. Options for the experimenter include with the earlier V2 systems using the IRF 520 that I'm using. If you shield the display cable, which is low-hanging fruit, you can reduce the birdies. So that's one of the things I'll be probably doing pretty soon when I can walk again. We have good solutions now that are implemented in 64-bit code for improving CW responsiveness and TR delays. ARRL's now come up with a 5-watt battery-powered version that you can carry very lightweight into anywhere you want to go for POTA or any other operations. $199, can't beat it for being cheap. This is now a possible platform for other projects, such as what I'm looking at, VHF, UHF, digital, SSB, CW, lower cost satellite work. What ARRL has done is push the cost of radios way down because he has climbed on to the curve of computing that continuously gets cheaper and cheaper and cheaper. Things that could still be improved upon. And I'm not convinced that ARRL is in favor of fixing all these things. The there's another forum on board, K9HZ, I think, I forget his exact call sign, with a much better power amplifier section. We could use a better power amplifier. The technique ARRL's using works, and it's cheap, but it could still potentially be improved. I believe that eventually people are going to put polarity protection right into most of these radios because it's so simple to do these days with MOSFETs. The risk to a $400,000, $500,000, $900,000 radio is just insane. So providing more protection. ARRL still has a little bit of an issue with 5-volt regulator needing to be a slightly lower noise, so that may happen. We already have 64-bit operating system and code available, and I suspect that most of us are going to migrate to that in the coming year. So we've really got a really nice radio particularly for the experimenter. It's probably not for the new technician licensee. It's probably a little bit confusing for them. But for those of us who really like to tinker with our radios, get right at the source code and understand how the thing works and what we can do with it, this is just a really fantastic radio. So I'm not sure I can hear the crowd, but that is what I've got to say. And I'm going to try to stop and see if there are any questions.
All right, well, this time we'll go ahead and see if there's any questions. Go ahead, Lee. I'll try to repeat them for Gordon.
Okay, do we have a URL for the Ukrainian transfer?
In your slides, did you have the URL for the Ukrainian transverter where they can purchase them from?
Oh, crap, I did the wrong thing. I do not, but that could be added, but let me show you how easy it is to find. Get out of this. What did I do? Get out of this. Click to exit presentation. Get that thing down. Get that thing down. Go to this. Go to eBay. not W Bay. And look for VHF, UHF transverter. Find the ones that are about 100. There it is right there. That's the one I bought.
Okay.
Yeah, the thing that
Okay.
what I liked, Lee, what I liked was it did both bands. It produced 10 watts, and the connectors on the back were BNC.
Oh, that's sweet.
I didn't like the SMA connectors, and this has a built-in attenuator. It is not set the way they say it is. Do not put 5 watts into this thing. On 2 meters, you'll blow it. 1 watt is all you need on 2 meters. I have not tried it yet on 70 centimeters. I understand it does need 2, 3, 4, 5 watts there, but on 2 meters, this is a cinch to use. Just 1 watt will do everything that you need. There is the adjustment for the right there, Gibby. Yes, that's the adjustment for the attenuator. I turned mine all the way down.
You mean the power output on the sBitX, you turned it all the way down?
No, I turned this all the way down, and I run the sBitX on mine. I'm producing about 0.8 watts, and that drives it to full power.
Wow.
So on mine, mine have drive setting of about 31 with my settings, but everybody's sBitX is different. So start very low, and then if you can't get it low enough, turn this down some. I think you'll have good success. For most people, if you can get it down to about half a watt on 2 meters and put that in, it will work fine, and then slowly advance the power up until you see that it's flat topped. The satellite guys tell you that the IMDs are a lot better at 5 watts than they are at 10. But this is a very nice transistor they use here. It's a RDS15 VHF1. It's a nice MOSFET.